Okay, so now we're here to look at using Gauss's law for charged insulators in cylindrical geometry. But now we're going to take a look at it. What if the charge isn't evenly distributed in that insulator? What if the charge is maybe a function of distance out from the center of the cylinder? Okay, so that's what we're going to take a look at now. So we're going to say that we have a cylinder. And again, this is going to be a very long cylinder, right? Okay, infinite. So we can treat it like it's infinite, and that way the ether will be nice and uniform. It's not really uniform because it gets weaker as you spread out, but you know what I mean. Nice straight field lines. So here we go. So we should carefully define our system, right? So we're going to say, so I have a infinitely insulating cylinder of radius r. Now, how do we want to talk about the charge distribution? Before I talked about the charge being like charge per length, right? And I could talk about charge per length, but that wouldn't help me when it came time to look inside, because when I'm trying to find the field inside, I care about how densely it's packed. Like if I did a cross section and it wasn't uniformly distributed, then I can't just do that simple ratio thing. So I'm going to need to define the charge in another way. And so I think what I'm going to do is I'm going to define it. Again, I can't talk about the total charge because it's got an infinite amount of charge. It's an infinitely long cylinder. I'm going to talk about the charge per volume. So instead of using lambda, I'm going to give you information in terms of rho this time, my charge per volume. Okay? So we'll say it's an infinitely long cylinder of radius r. And it's important for us that that charge distribution, it's a function of r. Okay, so it's like radially symmetric. Okay? And volumetric charge density rho as a function of r. Okay? So maybe we might consider a case where it got more densely packed as you head to the surface. So we could do like an example, for example, maybe rho is equal to, I don't know, some constant. Okay, I'm just going to use I can't use K because we use something else, K for something else. Let's just say we use a Greek letter, beta times r cubed or something, okay? So it gets more densely packed as r gets bigger as we head to the surface, okay? All right. What's this? This is case 4 for cylinders, I think. No, 1, 2, this is case 3 for cylinders. Okay, infinitely long cylinder, radius r, volumetric charge density rho. Okay, yep. And we want to find E at r greater than r. So outside. We'll do inside the cylinder for our next case. All right? So what does this look like? So first off, keep in mind that this cylinder does not end here, right? This cylinder goes on out to infinity. All right? All right. If I draw my coordinate axis, on my axis of the cylinder, kind of through, yeah, you know what I'm saying? All right. Let's see here. We've got a radius big R, and we're trying to find the E field strength outside. Right there. What's the E field strength at that point? Where this is little r bigger than big R. Okay, so on this diagram, which is like the end view, here's big R, and try to find my E field strength here. Okay, at little r bigger than big R. Okay, again, just a reminder, what does my electric field look like for this? We know that again, because it's all positive charge, E field's going to radiate outward. Okay, this does not have to be positive. We can do this problem with this being negatively charged, and the field lines just would go the opposite way. They would go in instead of out. It just flips the signs on things. No big deal. All right, and this would continue out. These are my E field lines. I probably should label them E. Well, magnetic fields later and gravitational fields. On this diagram, the field's going to radiate outward. Yep. Got that one. Good enough. Okay, we want to find the field here. So you know when we use Gauss's law, we've got to make our boundary go through that point. So we're calculating the E field at that point. We know that we want our Gaussian surface to enclose some charge, right? This is all part of how we choose our Gaussian surface. Integral over closed surface E dot dA equal to Q in over epsilon naught. Gauss's law for electric fields. So let's do our bubble. I want the bubble to go through here. Going to enclose that charge. Nice and symmetric. So if the same field strength here is here, it's got to be equal distance out from the center. Yeah. Okay, that's my bubble. This bubble is of an arbitrary length L. Okay. We know that the whole cylinder, of course, continues on out to infinity. All right, this is not a good way of symbolizing it, but I think you know what I mean. The cylinder continues on out, right? All right, we're just looking at a slice out of it. All righty, so here we go. Yeah, that's the setup. Okay, on this picture, of course, that Gaussian surface, it's an end-on view. It's going to look just like a circle here. That cross-section of the Gaussian cylinder. Gaussian surface. Okay. Let's go ahead and do this. Okay. I'm going to go really quickly. I'm going to presume that you have seen the previous video. But hopefully you see, hey, my area vector here, you say, when I go to find the flux through this surface, I recognize that really it's a set of three surfaces. I've got the left side, the right side, and then this curved part, the side of the cylinder, right? You know? So, it's like a cylinder. It's got its left end, the right end, and then this curved side surface, right? Now, the ends, there are no field lines punching in or out of these surfaces. So I don't have to worry about any flux. They contribute no flux to my calculation. I have to worry about the flux out this side. So, again, we said this is going to be the flux out the left end, the flux out the side, and the flux out the right end of that cylinder in this diagram. Equals Q in over epsilon naught. And we said, hey, the flux here, 0, 0. No flux out the ends, just to worry with the flux out the side. This curved ground side. So, having said that, how are we going to do? We're going to apply this equation here. I recognize that by symmetry, everywhere on that surface, the E field is going to be the same strength, that same distance out from the center of the cylinder. And so the E will be a constant. That angle between my area vectors that always stick straight out of the bubble, right? Straight out of my Gaussian surface. That's the same direction the E field lines are going. So I'm going to have a cosine of 0 degrees when I look at the dot product between the E field vector and the area vector. The angle between them is 0, cosine of 0 is 1. If this was negatively charged, the field lines would be going in, and the area vectors go out, it would be a cosine 180, be negative 1. Either way, it's a constant value that kicks out. So I'm going to kick out E and cosine of 0 degrees. And then what's left here, integral dA. And you say, hey, that integral of that dA, hey, that's just going to be the surface area for this blue bubble, for this side here, right? You say, remember the trick? We imagine this as being like that Gaussian surface being kind of like this, right? It's a cylinder surface around our charged cylinder. It's a cylindrical bubble. I'm going to slice it down the side and unroll it. And now I have a rectangle. The length of the rectangle here is that length L of the bubble. And this here, that's the distance around, right? That's that distance around there, okay? Which is just the circumference of the bubble, which is 2 pi little r. So my area, length times width, you realize that area is just going to be 2 pi r L. Okay, and cosine, this is just 1, put E. There we are. I just need to figure out what the Q inside the bubble is. And that is now the tricky part, right? Because the charge is not evenly distributed. So I can't just do a ratio or anything crazy like that. I can't just say, oh, it's all the charge. Well, how much charge is that? I didn't tell you the Q in there. We've got to figure it out. And I said I was going to do it with rho this time, didn't I? Yes, I did. All right, so here we go. Okay, so here it is. And what I want to do is I want to find the charge that's inside. And so, now I didn't tell you Q, we're trying to figure out that Q inside, but what I did tell you was my rho, okay? Now, rho, that's my volumetric charge per density, that's my charge per volume. So if I jot this down here, I would say, hey, rho is my charge per volume. Okay, now, because it's a function of R, right, I could say something like, we're saying we could do something like this, where rho is my dq over d volume, and I could just say, hey, the total charge, is that just going to be add up all the dq's from 0 till I have the total q. So I'm going to slice this up into a bunch of little dq's and add them up, right? But the only thing I have here to get Q is I've got my charge per volume. So I can take this and rearrange this, and couldn't I say that dq, look, rearranging this, is rho d volume, right? But the problem is that I have rho in terms of R, so that'd still be two variables, volume and R. So I need to slice it so I can get little d volume in terms of R, right? Ideally, I would love it if for each slice that I make of that cylinder, if each slice had a constant rho. So it was the same density everywhere on that slice. So I just take that density times the volume of the slice, right? Which means, since rho is a function of R, I want each slice to be at the same R value, the same distance from the middle. And that means my slices are shaped like what? Well, a slice here out of this insulator, one slice will look like this. Right? What does it look like in 3D? That slice will look like this. Okay, now I'm confused. All right, there we go. You know what I'm saying? What I'm slicing out is, yeah, I didn't draw that very well. Right, oh yeah, because of that, that's why. Okay, there we go. Okay, so what I'm slicing out is a cylindrical shell. Okay, this is all like dot, 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 dot. It's in the background there. Okay, a cylindrical shell. Let's go ahead and draw that, that's why. There we go, that's better. Okay, sort of, kind of. Okay, I think you get it, right? Look at inside the shell. So I have a cylindrical shell there. Okay, this one shell contains a certain amount of charge. How much charge? dq. We're going to make this infinitesimally thin little sliver, and then we're going to add up the charge, right? In these concentric cylindrical shells until I get to, how big? Big R, right? Until I get to the surface of that insulating cylinder here at big R. Okay, we're going to add up all the charge in all the shells. Okay, so that's the idea. Okay, so here we go. So each one of these shells, right? And I'm just going to come here. Hey, this shell contains a charge dq. It also has a volume d vol. But I want to do this in terms of rho. Rho is in terms of R. I need to write d vol in terms of R, so I have one variable for my integration. I mean, I could substitute rho d vol in here right now, but then it'd be an integral in terms of volume, and I got rho in terms of R. So let's rearrange this. What is the volume of one of these shells? How are we going to find it? what are we going to do? You know what we're going to do, don't you? We're going to say this is that cylinder, right? How are we going to find the volume contained in this cylinder? Not the volume inside, not this volume of the space in here. The volume of the actual cylindrical shell itself, right? How are we going to find it? We're going to slice it down the side, unroll it. What have we got now? Tell you what we have now. That slice, right? What we're going to do. Slice down the length of the cylinder and unroll it. What have we got? We've got this, right? But wait, it's got some depth. Right? What's the thickness of this? How thick do we want to make it? We want to take an infinitely thin little bit, right? This thickness is a little bit of R. It's a dr. Okay? So the thickness there of this guy is dr. What's this? That's this length L. This arbitrary length L that we chose. That's this length. Okay? What's this length? You say, that's the distance around here. When I slice it and unroll it, that's what was the circumference here of this one shell. We'll say is a variable length little r. So that is variable radius little r, 2 pi r. So what's the volume? Length times width times height of this rectangular solid. Rectangular solid. What's the term for that again? Parallelepiped or something? Anyway, point is, the area of the volume of this guy, you say, hey, that dvol, length times width times height, 2 pi r L dr. Okay? So, dq is rho dvol. dq, this is going to be my integral, rho dvol, but dvol, 2 pi r L dr. Now, what are my bounds? It's a new integral in terms of, this integral's in terms of a new variable now. So instead of being from 0 till I have all the charge that's in my bubble, now I'm going to go from q equals 0 to q is the full charge. I'm going to go from r is 0, adding slivers. Where do I stop? My boundary is here. I want all the charge that's inside the blue. Am I going to go all the way out to little r? No, I stop adding charge when I get to the surface of the cylinder, of the charged insulator. So I'm going to stop when I get to big R. So R equals 0 to R equals big R. Okay? Again, my bounds, they correspond to the old bounds, right? But they're in terms of, and they match the new variable. Okay, there we go. That's how I find the charge that's inside. Okay, and this is the Q in, by the way. What I call big Q here, this is the Q inside my bubble, right, which I usually make a little Q, don't I? Yeah, this is Q in. Let me write it that way. This is the Q in. Calculating here. All right. Okay, so where it says rho there, if this was uniform density, that rho and that 2 and that pi would pop out, just be the integral of r, and the L would pop out, be the integral of r dr, be 1/2 r squared, and I could go ahead and I could stick it in and do my calculation. Okay, if they had given me a uniform density and they give me rho instead of lambda, like I did on the previous examples, this is how I would handle that. You could handle it this way. Okay, but here I'll have to stick in whatever function they gave me. So if I was doing beta r cubed as being the function for density, as function of radius, I would stick the beta r cubed in there and integrate. Okay, and that would combine with the r there. I have r to the 4th, integrating r to the 4th, 1/5 r to the 5th. Anyway, and so on, I would continue on. But the point is, now that I have that, whatever this answer comes out to be, that's going to go in there for Q in. Then I'll move my 2 pi r L over. The L's are going to cancel. This is a constant. It's going to kick out. So I have an L on this side, an L on this side. The L's will drop out, which is good because I invented that variable. So it goes away. And I'll have my answer. Okay. So what I get depends on what this function is. Just for the heck of it, I'm going to work it out for beta r cubed. Okay. So let's work it out for beta r cubed. So continuing that, I'm just going to go ahead and give myself some space. Okay, my Q in will end up being, move all the constants out, 2 pi L integral, rho is beta r cubed. And I still have an r dr, okay, from 0 to r. Okay, the beta would kick out and I'd have r to the 4th. Sure, why not? 2 pi L beta, all right? Okay, now the integral of r to the 4th dr. You know what I'm saying? That r is from the original thing. This is just the beta plugged in. Okay, good, the rho plugged in. Okay, so now what have I got? Well, you say the integral of r to the 4th is 1/5 r to the 5th. And when I plug in, you know what I'm saying? It's going to be 0, and then when I plug in the r, right? And so you see I'm going to end up with 2/5 pi, wait, yes, right? L beta big R to the 5th, right? That's what I'm going to get. Okay, that would be my Q in. Okay, and so this will go in there. I'm just going to go ahead and draw that in. So I'll have 2/5 pi L beta r to the 5th. When I move this over, you notice that this is big R, right? Because I stop adding charge when I get to the surface of the cylinder. So I'm finding the field outside. So this R is a variable R. That's the distance outside. So these R's are not going to cancel or anything, right? So when I move it over, my answer is going to be in terms of 1 over little r, okay? Which you may recall we said that tends to be the case for uniform cylinders, that our field outside is proportional to 1 over r. So looking at this, let's see, can we cancel some stuff before I move it over? Yeah, look, this 2 and this pi and the L, right? So I'm going to end up with an answer that'll be beta r to the 5th, yeah, over 5 epsilon naught, yeah, times 1 over r. Okay, that's going to be my answer for this particular problem, where the density would happen to be given by this function. Okay, with a different function, we'll get a different looking answer at the end with this technique, right? And in particular, how we slice this up, slice to little dqs. We're choosing this shape because it makes it so that we have a constant density, because it's a function of r, so we have the same constant r for each slice, each little dq that we make. All right, and how we found the volume of that, so we could use the rho, the charge per volume. That's the important part of this. All right, okay, hey, what comes next? Same setup, but now we want to find the field strength inside, right? How is this going to be different? You say, well, the way it's going to be different, and I feel like not doing a whole new diagram, I feel like just talking about it on the old sketch. Is it okay if I draw on the old sketch? It's going to make a mess, or should I draw over again on the other board? I hate to draw this all over again and make this film really long, but I want to make sure it's clear, you know? Well, I'm going to try writing on the same board, right? So if we did same setup, but it's going to be case 4, I'm just going to draw all over this. Case 4 is going to be same, but find E at R less than R. So inside the charged insulator. So maybe we want to find the field strength. Now I'm going to try to color code it. Is this brown look significantly different than this orange, I hope? Okay. Say now I want to find it here at a distance little r that's smaller than big R. Okay, so I'm inside. All right, find the field strength there. What's going to be different? Well, trying to find the E field strength here, at like some point there, little r, where little r is smaller than big R. I'm inside the cylinder. all right, for case 4 here. You say, hey, what am I going to do? I'm going to make a Gaussian surface. Where's the Gaussian surface got to go? It's got to go through the position I'm trying to find the E field at. My surface is going to go through there. So I'm going to do a little bubble. I want it, because density is a function of R, I want it to have a constant density on each slice. Yeah. And we're getting ahead of myself, sorry. We're going to make our circular, there we go. Okay, when I extend this out, it's going to be a cylinder. I'm going to draw it a little shorter than this one, all right? It's just so, you know what I'm saying. Ooh. Yeah, I'm going to draw it shorter so it doesn't, you know what I mean? So here's my new Gaussian surface. Here, make it nice and thick. Here we go. Here we go. Here's my Gaussian surface. That didn't look so good. You know, it's supposed to be vertical, right? Anyway, okay, that's my bubble. It's inside, right? Inside the insulator. Okay, and it's got a radius little r. Okay, there in the brown. Okay, so there we go. So that's it. Would you not agree that this left side is going to look identical? Right? It's going to look identical. Again, I'm going to have no flux out the ends of this blue cylinder. The only flux is out the side. So bam, bam, those go away. Out the side, you would agree that my area vector is pointing straight out, parallel to the E field lines here. Same thing here. My area vector goes out of my bubble, my Gaussian surface. You say, hey, the field lines are going parallel to it. You say, it's going to be cosine of 0 everywhere on this surface, on the curved surface, nothing out the ends. And so again, I'm going to have E cosine theta 0. Those will pop out. Integral the area. What's the area? Hey, the area of this, again, if I slice it down the side and unroll, it's the diagram's gone. It's just a rectangle with a length L. Okay, I'm calling this L now for this problem, right? I chose arbitrary L, you know what I'm saying? And a distance around is 2 pi little r. So again, it's going to be 2 pi r little L. That's the area of the bubble. Okay, this is the bubble, the Gaussian surface, the blue bubble, right? So it's the same left side, the right side, Q integral. So I got to find the Q in. This is where the difference is going to come, but not quite yet. I'm still going to use my charge per volume. I'm still going to do dq over dvol and say, oh, dq will be rho dvol, right? I'm still going to add up all my dq's and get my total q and substitute in rho dvol. The problem is, what's the volume of this? Well, how am I going to add in dq's the same way? I'm still going to do cylindrical shells like I did before. It's just my shells here. They're just going to add up all the charge in there the same way I did before. What's the difference? I only want the charge that's inside this bubble. I don't want this charge out here that's outside my Gaussian surface, because it does not contribute to the total flux, because any flux from a little positive charge here would go in and then go out the other side, right? From charges outside the bubble. So I want to add these guys, but I want to stop when I get to little r is equal to the radius of my bubble. So I'm just getting the charge in the bubble. So when I do this, the difference for the brown case, for the case 4, is this upper bound. I'm going to stop when I get to little r. So what that means, little r, right? What that means is when I get down to here and I do this integral, this is not going to be a big r to the 5th. It'll be a little r to the 5th for this case where I have beta r cubed as my example, all right, of charge density. It'll be little r to the 5th. So now when I put this in here, I'll have little r to the 5th. Now this r will cancel one of those r's. Didn't do it before because they were different r's. Now this will cancel one of those r's. And this will end up being what? This is r to the 5th, and I cancel one of them. This will end up being r to the 4th. Okay? So what I'll end up with is this. Yep. This will be my E field inside. This is the E inside. Now, proportional r to the 4th. Okay, very different than the field outside, which was proportional to, well, Okay, not that different, but which we want to say is proportional to 1 over r. Outside, inside is proportional to r to the 4th. If I had to do some kind of a crazy graph for this, right? Here we go, crazy graph coming right up. And you say, hey, here's r, distance out from the center. Here's my E field strength right here. That's big R. What's my E like inside? We said, hey, that ended up being proportional to, it was 1 over R, wasn't it? Was it 1 over R? Oh my gosh, now I've already forgotten. Oh, it was 1 over R. Of course it was 1 over R. Yeah? No. What did I do? What did that E field? Oh, it was R to the, oh, no. Yeah, it was 1 over R. Uh-oh. That doesn't sound right. Why would it be proportional to 1 over R? As R got bigger, the field strength gets weaker. That's not right. Did I do something wrong? When I did the first calculation that I've now erased? No, it was fine. I'm just remembering what I had there wrong. No? No, that was fine. That was fine. Right, that was fine. No, that was fine. Oh, because that was outside. Right, oh, it was outside. Oh my gosh. Okay, that's so silly. Sorry, yeah. First thing I do is outside, and that was a 1 over R. Inside is proportional to R to the 4th. So inside, it's some really steep curve, right? Proportional to distance to the 4th. It's going to like shoot up, right? And this is E is proportional to R to the 4th for this case. But when I'm outside, it's E is proportional to 1 over R. There we go. That's it. And those two functions should stitch together perfectly at the boundary. I wish I hadn't erased the old answer. That really would have been nice, because then we could put in that value, R equals big R, into both and see that we got the same value. We will get the same value. They'll stitch together nicely there. All right, so that's it. Okay, so that is my E field for non-uniform charge density for both inside and outside the cylinder. All right. Hey, what's left? What's left is we could talk about what if these were conductors? Well, if I have a cylindrical conductor, the charge is going to spread out on the surface of the conductor, right? Because that's what charge does. And so inside, my E field would be 0 if I had a closed boundary inside, right? So am I going to squeeze it in this corner? You betcha. So if I had a cylinder, a charged cylinder, right? That is a conductor that we're talking about. I've got a conducting cylinder. Okay. My charge is going to end up at the outer surface. I'm not going to have any, so inside will be nice and neutral, right? Remember that? That's the case. And so why? Because in a conductor, the charges can rearrange themselves, and they will. The electrons are free to move. They'll move until the force on them is 0. If the force is 0, since E field strength is the electric force per charge, right? If the force is 0, the E field is 0. So inside, once it gets to equilibrium, we know that inside this guy, E is 0. But let's say it's positively charged. That positive charge will be spread out plus at the surface of the metal. You know what I mean? Okay, all along the surface on the outside, right? And so I'll get field outside radiating out. That's assuming it's positively charged. Obviously, if it's negatively charged, right? And this is an infinite cylinder again. I'll have a nice uniform field radiating out. Okay. And so when I'm outside, again, I could talk about charge per length, per linear meter going along, and the calculation will look just like before when I'm outside. When I'm inside, the E is 0, and that's all there is to it, okay, for a charged cylinder. If I have nested cylinders, right, nested in each other, we talked before with the spherical geometry, but if I had nested conducting spheres with stuff inside, about how that would induce charge to separate in the metal spheres, right, the spherical shells to the outer and the inner parts. Same sort of thing would happen if I had cylindrical shells. I could induce separations of charge. I have charge on the inner surface and outer surface if it's a hollow shell, right? So we do that same sort of thing, but inside the metal itself, the E field would be 0 inside each of those cylindrical shells. So we could go ahead and do that. That sounds like a great problem, doesn't it? But we could do a problem like that, and it should be fun. All right. Hey, that's it for cylindrical geometry. What's left? Planar geometry. So that's like if I have say I have something like a sheet. Okay, now imagine there's charge distributed all throughout this thing, right? Throughout this plane. And let's make this, and you say, again, it's gonna make a nasty shaped field unless this is infinite sheet, infinite in all directions, extends out infinitely. Then we could go ahead and find our field outside or some depth inside perhaps, right? This insulating sheet of charge if the charge is distributed evenly. We could do problems if it's not distributed evenly, if it makes more densely packed heading to the surfaces, right, of this sheet or something. We could talk about if this was metal, if it was a conductor, and the charge was smeared out, it would just be on the top surface and the bottom surface instead of being distributed throughout. We can talk about dealing with that. We'll do that next class. All right, so, and that'll be the last topic for this unit, okay, is dealing with planar geometry, so geometry of planes of charge. Okay, and that's the last thing. All right, see you later.